Hi children. So this is T.S. Rao, Sri Chaitanya's NEET Sankalp 2.0 program, and today I am going to discuss the two important chapters which are similar chapters, electric charges and fields and gravitation, and most of the topics in both the chapters are the same. So first we will see that about the concepts. While doing the concepts itself, numerical concepts also I will give it to you, and accordingly you can follow that, right. So I will focus more on concepts today, and how to apply and all other things we will discuss, right. Now coming to the point here, first electric charges, we will see that in the electric charges and fields and gravitation, first part is the same, right. So first I am doing that here, and electric charges and fields, the first we are going to see that in this about the charges, right. Now you can see first one, the first topic in this is, in general every matter is electrically neutral. This body is electrically neutral, this body is electrically neutral, our body is electrically neutral. It does not mean that actually we do not have the charge particles. We have a charge particles, but equal in number of positive and negative ions of same charge, particularly protons and electrons, and equal number of protons and electrons will be there. Equal number of protons and electrons will be there. Therefore, the net charge is equal to 0. But we can impart the charge. And what is the mechanism to impart the charge? There are three different methods will be there here. One is a conduction, one is a convection, one is a induction, the next one is a friction method. So I will repeat once again, conduction, induction and friction method. By any method, so first of all we can see that here as is a neutral body, and when electrons are added to this, it gets a negative charge. And how much of the negative charge depends upon the number of electrons added. Similarly, from a neutral body, when certain number of electrons are detached, it gets a positive charge. How much of the positive charge also depends upon the number of electrons detached. Protons cannot be detached, protons cannot be attached, they are with strong forces inside the respective nuclei. Now let us see that here. When the two charges are created, let us take that in the nature fundamental charges are positive and negative, and a fundamental positive charge particle is a proton, fundamental negative charge particle is electron. The charge of electron is equal to minus 1.6 into 10 power minus 19 coulomb. Charge of the proton also equal and opposite. Now first of all you can see that here, and when this is our neutral body, assuming that it is 100 electrons we have and 100 protons we have. From this let us take that here certain two number of electrons are detached. It gets a charge equal to 2 times to the charge of the protons, right. So now let us take that here, if n number of electrons are detached, then how much of the charge it gained? How much of the charge it gained? Q is equal to plus or minus Ne. That is, charge is always quantized, and the charge is always integral multiples of number of electrons, and n be the number of electrons attached or detached. E is the charge of each electron. Accordingly we can calculate. Again, when electrons are detached, it gets positive charge, electrons are attached, it gets a negative charge, right. So I am just giving one formula here, and first formula of this chapter, and I give one important model, find number of electrons. So number of electrons, and to impart a charge of 1 coulomb here, that is number of electrons equivalent to create a charge equal to 1 coulomb. So therefore here N is equal to Q by E. The same formula here, Q is equal to 1 coulomb, and which is equal to this you can write as 6.25 into 10 power 18 electrons. Now the next one, find the charge gained by a neutral body when this many electrons are added. 4 into 10 power 16 electrons are added to a neutral body. The same concept here, and Q is equal to plus Ne, where plus N be the number of electrons added and E is the charge of each electron. And if you multiply that, you are going to get that here minus 6.4 in 10 power minus 3 coulomb, which is minus 6.4 millicoulomb. Next, this is about the first part. Now the second concept, if you see that, once the charges are created, you all know that here like charges repel and unlike charges attract. So attracted by a certain force or repelled by a certain force, the magnitude of the force can be estimated by the Coulomb's law. And according to Coulomb's law here, the force between the two charges, directly is proportional to Q1, Q2, inversely proportional R square, and therefore F is equal to, you are getting that here, C into Q1, Q2 by R square. What are Q1 and Q2? The charges of the two particles r with the distance between them. So, accordingly we can write it as, and this C depends upon what actual medium. Whatever the constant here, proportionate constant depends upon the medium. If at all the medium is a free space, then 1 by 4 pi epsilon naught Q1 Q2 by r square. If at all the some medium is there, some dielectric medium is there, like insulating medium, if it is there, then 1 by 4 pi epsilon. Epsilon naught is the permittivity of the free space, epsilon is the permittivity of the medium. Permittivity of the medium can be written as, and how many times to the permittivity of free space we can write it. So, which is equal to k times, which is called the dielectric constant. Dielectric constant is different for the different materials. What is the dielectric constant for a free space? Either air or vacuum, 1. For a metals, almost infinity. So, accordingly we can calculate here, and what is the force between the two charges with a medium, force without the medium here, and we can see that from these two what you are going to get, what is exactly k value also we can calculate. Force with a medium is equal to force without medium by k, that is whenever the two charges are separated by a free space, certain force will be there. If at all that is filled with a completely medium here, and the force becomes 1 by k times to the original force. So, we can write it. Next, and what is the 1 by 4 pi epsilon naught is this. Coming to the next, and force being a vector. Force being a vector, for example, if one charged particle is under the influence of many charges, one charged particle under the influence of many charges, then how to find out the net force experienced by it? Net force is nothing but what actual vector sum of individual forces, and we need to find out what are the forces that are here, and one simple question that we have here, an important model of course, and three particles A, B, C of same charge Q, and which are three corners of a triangle of side L, and what is the force on only A I am asking. All are Q, Q, Q only, all are right charges and equidistant. Therefore, this Q is under the influence of repulsion force by this, force on A by C, the force on A by B, and both are repulsion because like charges, and the two forces that experienced by A. Therefore, the net force will be equal to, because this force and this force, resultant will be acting here, and the resultant from the parallelogram law of vector addition from the motion of body in the plane that you know, and R is equal to 2f cos theta by 2. When do we use this? And whenever the two forces like force F1 is equal to F and force F2 equal to F, which are acting at an angle theta. Now, the resultant force we can calculate using of this formula here, R is equal to 2f cos 60 by 2, where theta is the angle between the two vectors, which is also 60 because equal a triangle. So, accordingly we can calculate, and what is f value is known, q square by l square, and we can substitute here. Next, coming to the point here, very interesting question. Two identical charges, two identical particles are with the charges 6 and minus 6 are at a certain separation attracting each other with a force 36 Newton. Find the force, this is a previous NEET question, and find the force between them when they kept in contact and separated to the original distance. These are the two particles identical size. If these two particles are having the different charges, they are under attraction force because one is a positive, one is a negative. Here the charges are, one is positive and one is a negative. Then they are under the influence of the forces, like how much of the distance we do not know, the force is given. Now, these two charges are kept in contact and separated to the original distance. Definitely the charge changes, charge distribution takes place, and because of that force also changes, the separation is the same. And what are the charges before, what are the charges later, we need to know. So, the charges before already given, charges later to be find out here. So, for this, when the two identical charge particles, this formula remember, whenever the two identical size, the two particles are kept in contact, and this charge is equal to say q1, this charge is equal to q2, and these two kept in contact. So, definitely the charge of these two distribute, and so that the net charge of this one q1 dash is equal to q2 dash is equal, the formula is equal to q1 plus q2 by 2, average of those two. And earlier the charges are 4 and minus 6, and accordingly we can see that minus 1, that is charge of each particle become minus 1 only. Earlier the charge of this one is 4 and minus 6, now the charge of each one is equal to minus 1 and minus 1, and earlier it was the attraction force, now it is the repulsion force because both are negative, right. So, f by f dash is equal to q1 q2 by Q1 dash, Q2 dash, I substituted and we got that F2 is equal to 1.5 Newton repulsion force. Why repulsion? Both are like charges. Earlier they were unlike, because kept in contact, charge flows from one to another until they come to average of those two, provided identical in size. If they are not identical, we will see that. Next, here, and equilibrium of charges. There are some questions and we will see that some more points here. Now, equilibrium of charges. If at all one charge particle is under the influence of many charges, sometimes that particle experiencing individual forces, but the net force experienced by the charged particle may be 0 under the influence of many forces. Not compulsory that those forces are electrical forces. Sometimes other external forces also will be there. So, based on that we have one or two examples and we will see that. Equilibrium. Equilibrium in the sense what actually, and the net force must be equal to 0 here. And see, F net is equal to 0, then system is said to be the, and equilibrium, that too it is what actually the translational equilibrium in our case. We do not have any rotational at this moment, right. So, now let us take that here. These two are the two charges, capital Q, which are known here, and asking that, and the distance between them is L is given. Asking the question, find the Q, some third charge Q, for a system to be in equilibrium. The Q is placed at some point between them. What must be the value of this Q is asking. What must be the value of this Q is equal to how much is asking for the system to be in equilibrium. If in the absence of the small q, you know, these two cannot be in equilibrium, because this experience a repulsion force by this also experience a repulsion force by this. But when the third charge is kept somewhere in between, that we need to calculate. At what distance also we need to calculate. What must be the value of q also, so that the system in equilibrium, for which you can see that here. And first of all, the small q to be in equilibrium, it should experience equal and opposite forces. Like you see that F1 is equal to minus F2. From this you are going to get that exactly, because here the product of the charge, here the product of the charge is same. As the product of the charge is same, distance also supposed to be the same. Here the distance and here the distance is same in sense. This must be equal to L by 2, this must be equal to L by 2. That means a small q to be placed, exactly midpoint for the system to be in equilibrium. Then what must be the value of that? Okay, we got that position. What must be the value of this? And we can also calculate with that. You can find out here q to be in equilibrium. Here I am taking the second part. First one, small q to be in equilibrium, I took that. Now second one is, if this is also to be taken in equilibrium here, and the net force on this must be equal to 0, force experienced by A by C, force experienced by A by B must be equal and opposite, and net force, you can see that here I substituted force between A and C I calculated, and between A and B I calculated, you know, the A and B, the A and C, and ultimately you are going to get that here. So, small q is equal to minus q by 4. Okay, we got that position as well as the charge. Coming to the next, and this is another application of equilibrium. Children, let us take that here. These two are the two pendulum bobs. Let us assume that they are neutral particles here. This is a neutral bob, this is a neutral bob, both will be like this. But some charge is given to both of them, q and q given to them. Then what happens here? Because of the repulsion, they go to new position of equilibrium. Earlier they were in equilibrium under the influence of tension only. Tension is balanced with the weight. But once the charges are given, they also experience one repulsion force, due to which they get separated and they go to the new position where again they come to equilibrium. And the conditions for the equilibrium, you can see that different cases here. And in this case, equal charge is given and they go to the new separation is equal to small r, for which this is to be in equilibrium. This tension is a breakup into the two components, T cos theta and T sin theta balanced with the electrical force, T sin theta balancing with the electrical force, T cos theta balancing with the mg, and tan theta is equal to, just you divide these two, Fe by mg. What is Fe? You know, Fe is equal to Coulomb inverse square law k q1 q2 by r square. If at all some medium is there, k value will be given. If at all no medium, just simply 4 pi epsilon naught between them. So accordingly you can take that here, we can. And one more here, this complete system is placed, if this complete system is placed in a liquid, then weight of the bodies in a liquid, weight of the bobs in a liquid changes, and weight of the bobs in a liquid changes, which is equal to mg into 1 minus rho L by rho B. This is what actually apparent weight. We also call it as the apparent weight in liquids, right children, and this is equal to 1 by 4 pi epsilon naught q1 q2 by k r square. What is the k? Dielectric constant of the liquid in which the two bobs are placed. The system is completely placed in the liquid. In that case, k value changes because medium change, and naturally that density because of that, and apparent weight also changes, and the tan theta value also changes. Earlier the tan theta without medium, and this is with medium. Now here I want to add, I did not mention here, I write it clearly. If gravity is 0, if gravity is equal to 0 in the first case, if at all the gravity becomes 0, what actually here, something by 0 is infinity, therefore tan theta is infinity, therefore the theta will be equal to how much it is, 180 degrees. Theta will be 180 degrees. Therefore what actually here, the pendulum bobs will go like this, and what is this force here? Electrical force, and this also electrical force balancing with what actually the tension. Just T is equal to Fe only, provided, remember, provided gravity is ignored, right children. Now we will go to the next application, next cases we will see that. Next, this is also one of the important problem in the Coulomb's law. 2 point charges plus q and minus q are placed here, and they are under the influence of certain force here, force F, and if 25% of the charge is transferred from here, that is q by 4 charge is transferred to this, and how much of the charge is left? 3q by 4, and how much of the charge the other particle gets? Minus q plus q by 4, which is equal to minus 3q by 4. Earlier both the charges are q and q. Now the new charges are what are q and minus q. Now the new charges are what actually 3q by 4 and minus 3q by 4, and only the charges changes according to the force changes, and F by F dash new force, original charges q and q. Now the new charges 3q by 4 and 3q by 4, only magnitude we are calculating, direction we know according to their charges, like sign of the charges we can say that. F dash is equal to 9F by 16. Is it attractive force or repulsive force? Earlier it was a attractive force, now also attractive force, and this also we can write as attraction only, attraction force. Now coming to the point here, electrical, this is about the Coulomb's law children. Now electrical field, in the next concept you see, electrical field and intensity, and electrical field and intensity here, and different cases will be there for a point charge, and the electrical field produced by the point charge, because electrical field nothing but here the region around the charge body or charge particle in which the influence of the given charge is felt, and the strength of the field at a point is called the intensity. The intensity varies from place to place, depends upon many parameters, and if you take a point charge here, as the distance increases, so naturally that intensity decreases. E is inversely proportional to r square, E is directly proportional to q, therefore E is equal to kq by r square, the magnitude. If at all the vector form is given, we can go for the same thing here. If the charge q is placed at a position A, charge B, I mean at a point B, you want to find out the intensity, where the positions of A and B are given, and the vector form of electric field intensity is this. Now that is all about the electric field intensity, but one thing I want to tell here, with respect to the positive charge, if at all you take that here, I gave the diagram, and plus positive charge, the direction of intensity is away. With respect negative charge particle, direction of intensity to be taken as towards. While doing the problems, we can apply the sign conventions. With respect to positive charge, away, with respect to negative charge, towards. Now electrical null point, the next concept is the electrical null point. Same thing, equilibrium of charges, indirectly the same concept here, the point at which under the influence of many fields the net field is equal to 0, that is called the electrical null point. Now electrical null point, let us take that here in case of two like charged particles. In case of only two like charged particles I am giving. If at all many are given, how to do that? One problem will see that two like charges are given, and this place what actually this particular charge particle will give the intensity away, and this intensity away, both are equal and opposite gets cancelled. The net intensity will be 0 at a distance x is equal to this, x from here. Next, same thing in case of unlike charges. is a very common formula in many chapters here in the gravitation, the magnetism, in the moving charges and all other cases. And in case of unlike charges, the distance at which the electric field intensity is 0, it is always away from the lighter charge. Lighter charge can be either negatively charged body or positively charged body. Let us take that here at a distance x. What is that? X is equal to r by under root q2 by q1 minus 1 is the magnitude of this one here only. Only magnitudes to be taken here. Here is also only magnitudes. Okay. Now, that is all about the electric lines of force in case of point charges. No sir, if at all many charge particles are given, simple example I will tell you here. In this case you can see, for example, let me take that here, 4 charge particles are kept here. 4 charge particles are kept here, and this is equal to plus 2q, minus 2q, minus 2q. So, definitely the electric field intensity is equal to 0, here E is equal to 0, net electric field. Or else if you take that here, the same charges are given, but positions of the charges change. This also become plus 2q, this is minus 2q, this is minus 2q. The electric field intensity at the midpoint, is it equal to 0? No. The net electric field at this place E is not equal to 0. The reason here, in this case, and electric field given by this positive are equal and opposite, they get cancel each other. They are getting cancel each other. Is get cancel here, this get cancel, this gets cancel and cancel here. Net field is equal to 0. But here net field is not equal to 0 because intensity given by this one is down. This also in the same direction, attractive. This is a like this and this also like this. Therefore, the net field will be equal to here E. It is not equal to 0. Okay. According to the positions of the charges and all other things we can estimate. Coming to the next, see, electric dipole. Till now we discuss electric field by the point charge. Electric field by the point charge. Now we are seeing that here electric dipole here. In case of electric dipole, it is a, what is a dipole? It's a system of 2 charges of equal magnitude and opposite sign. And a negative charge and positive charge, if the system of the 2 charges like minus q and plus q are placed at a certain distance here, so definitely, and it will form one particular situation that is called the like a dipole, where negative charge to the positive charge. The distance between them is the length of the dipole, which is equal to 2a, which is a vector. Remember, length of the dipole is a vector. Is a vector. Length of the dipole is a vector. Here, it is always from negative charge to the positive charge, right? So, dipole moment is equal to here, how much it is? P bar is equal to 2a into q, where q is a charge of either positive or negative magnitude of the charge, and p is equal to 2aq, is always from negative to the positive. Now, coming to the point here, this dipole also create the field around. What will be the field for a dipole here? And particularly we take the 3 different points here. This point is the axial line, the line joining the 2 charges, the line joining the center of the dipole and perpendicular to the axis called the equatorial line. We will take the 3 different places. What is the electric field intensity here? What is the electric field intensity? What is the electric field intensity? If at all you know the formula directly, you can answer direct questions. Okay? We will see that we have 1 or 2 models of the questions also. And first of all, electric field by the dipole here on axial line we are discussing first. On axial line. On axial line, how to calculate in sense? This is negative charge, positive charge. This place electric field intensity. And due to this positive, away. Due to this negative, towards. If at all as a derivation you want to know that, just one step I gave that here, and the net field at this place is equal to intensity given by this point charge, intensity given by the point charge, both are opposite. The net field is equal to, magnitude of the net field is equal to here E1 minus E2. What is E1? KQ by R minus A, where R is the distance at which you need to find out the intensity, right? I substituted and we got that intensity at point A is equal to this. Now, but most of our questions are with the short dipole. If the length of the dipole is not given, mandatory to take that is a short dipole. So, in that case, and what will be the electric field intensity in case of the short dipole, where A can be ignored, R square whole square, R cube, and R cancel, which is equal to 2p by R cube. intensity due to the dipole on axial line directly proportional P inversely proportional R cube. Point to be noted here, it is the only for a short dipole. And now the same thing here, and what is the electric field intensity due to the dipole here at this place on the axial line is a parallel to that of this, both are in the same direction. Next we will see that about the equatorial line. On equatorial line of the dipole, children, this is the dipole on equatorial line, the intensity at a point is equal to K into P by R square plus A square. This is equal to 2A. This distance is equal to 2A here, this is equal to R here, and what is the electric field intensity? Due to this positive is away, due to this one is this side, the net field will be like this. The net field, electric field here to be find out is this. For a short dipole again, A to be taken as 0 and Kp by R cube. Again here is also the intensity at a point on equatorial line opposite to the dipole moment. On axial line is parallel to the dipole moment and here anti-parallel. Here E is inversely proportional to R cube, directly proportional to P here, and E equatorial line will be half of the E axial in magnitude. Okay. Next, at some point, arbitrary point, let us take that here, at some any point here which is at an angle theta. So you remember this formula, Kp 3 cos square theta plus 1 under root by R cube. Theta is equal to 0, axial line again. If you take a theta is equal to 0, axial line, and a theta is equal to 90 degrees for equatorial line. Okay. Next, direct problems will be there here. Now the dipole, once it is placed in the electric field, once the dipole is placed in the electric field, children, here this is the dipole which is placed in the electric field. It is under the influence of external force, and force on the charge particle is this, and force on this charge particle is equal to this, and the net force is equal to 0. What is the force on the charge particle here? This F is equal to how much? Any charge particle placed in the electric field, it expends a force F is equal to magnitude of this one is equal to EQ. The same thing here is also equal to that of EQ. Both are forces equal and opposite magnitude because the field is uniform. If it is a non-uniform, we have one numerical and we will see. And net force is equal to 0, and net torque is equal to how much is not equal to 0. If you leave it like this, what actually this force and this force are acting opposite direction and create the torque. Rotational turning effect is produced, and with respect to the axis passing through the perpendicular plane of this, and the system is oscillating like this. Okay, and it explains the torque here. The torque is equal to P cross E, Pe sin theta is a magnitude. And potential energy also I am giving here, potential energy, because it is able to move under the influence of electrical force, which is a conservative. Potential energy concept will be arise. Potential energy of the dipole in the electric field is equal to minus Pe cos theta. Now what is the time period of oscillations of this dipole? Time period of oscillation says whenever the dipole is placed in the electric field and slightly displaced, in that it is in the stable equilibrium. It is in a stable equilibrium, net torque is equal to 0. If you slightly disturb from here, what actually here oscillates? The time period of oscillations is equal to 2 pi root I by Pe. P is the dipole moment, E is the electric field intensity of the external field. Next, this concept is done. Now the next one is a force between the two dipoles. If at all the two dipoles are placed such that they are in the same line, they attract each other. The attraction force between them is equal to the attraction force, because it is a negative charge and this is a positive charge, this is negative charge, there will be attraction force here. This force will be this side, this force will be this side here, and what is the force of attraction we can calculate. If at all they are opposite to each other, force will be repulsion. If at all one dipole is like this, one dipole like this, and repulsion will be there here, but here is attraction. That force is equal to K into 6 P1 P2 by R power 4. Remember children, here the force is, in this case, force is inversely proportional to R power 4. This is a PYQ. Force is inversely proportional to R power 4 in the magnetism, that is a PYQ. Same magnets also, the same concept it is. When the two magnets are placed, that question is there in the previous NEET. F is equal to K into 6 P1 P2 by R power 4. And if at all the two dipoles are placed parallel to each other such that the perpendicular distance between them is equal to R, and we write F is equal to K into 3 P1 P2 by R power 4, right. So the simple concept here and formula based topic, please go through that. Next, quadrupole. Quadrupole is a system of two or more dipoles. One of the simple case will discuss first of all arrangement of the two dipoles I gave you, and let me take that as a minus 2q and plus q and q. This minus 2q can be assumed to be a combination of the two charges of minus q each, and it is creating one dipole. This is another dipole of moment p and p, both are angle theta, then resultant dipole moment is equal to that. This is also called as a moment, like electrical dipole moment of quadrupole, 2p cos theta by 2 here in this case. From the vector concept only we can write it. Next, so this is about the end of the dipole and quadrupole here. Now electric flux and Gauss law, we have another topic here and we will see. Electrical flux, children, here. What is electrical flux? Flux through a given surface is equal to, here phi is equal to E dot A, which is called EA cos theta. And flux through, what is the flux in sense? The number of, it is a measure of number of electric lines of force passing through a given area. More number of lines, that is, if the field is more number of the field, more number of lines will be there, and more electric field intensity will be there, and definitely what actually flux will be more, and the flux is equal to EA cos theta, E dot A, we can write it, where flux is a scalar and SI unit of this one is equal to this. Let us assume that here this particular surface making an angle theta, whose surface area make an angle theta with electric field intensity. So in that case we can write this electric field intensity here, and we can write it as EA cos theta. Okay, and we have some example also for this, any kind of example. For example, I will take that here. Here electric field intensity E is equal to 2I plus 4J Newton per Coulomb, and what is the flux through the given area, and area vector which is equal to, area is equal to here 4 meter square along y axis, then flux is equal to how much, and flux directly you can write as E dot A, E dot A is equal to Ex, that means x component here is 2, here no x component, here we can write as 0, plus here the y component is 4, and this complete y component is along the y, area vector is along the y axis. I gave you here 4 into 4, which is equal to 16 units, we can write it. Electric flux depends upon the surface that you take it. If at all the surface is in the xz plane, the direction of electric field direction of aerial vector will be along the y axis. If in the xy plane, direction of area vector will be along the z axis, and electric field intensity, whether it is a perpendicular to the aerial vector or parallel to the aerial vector, opposite the parallel vector, it will be there here. If at all they are in the same direction, if the lines of force are leaving any surface, the flux to be taken as positive because E and A are in the same direction. If they are opposite direction, the flux will be negative. We have 2-3 examples, we will see that. Now the next electrical flux experimental concept, that also we have Gauss law, and to explain the Gauss law here, we imagine one particular surface which is called the Gaussian surface. Now what is the total flux linked with a closed surface which is called the Gaussian surface, which is equal to 1 by epsilon 0 times to the charge inside that. The total flux through a given surface is always depends upon the number of charges, I mean the total charge inside the surface here, and which also can be said that here E dot dA integral, where E is the electric field intensity, if it is a variable or a constant, accordingly we can write it. This particular formula is only when E is constant. If this is a area where we can say that here E changes with area. Now, and this is a one simple theoretical point here. Electric field intensity is a resultant field due to all the charges. For example, here if at all electric field here, you want to find out the electric field here, let us take that here this is a Gaussian surface, and here is a one charge particle, here is a one charge particle, here is another charge particle, here is a one charge, here is a one charge, like many charges are there here. But electric field intensity at this place is due to all the charges. Electric field at this place is due to all the charges, the charges outside as well as the charges inside the Gaussian surface. That is what actually mentioned here, both those inside and outside the Gaussian surface. But the next point you see, electrical field due to the charge outside the Gaussian surface contributes 0 net flux through the surface, because as many lines due to that charge enter to the surface leaving also, and how many lines are enter is equal to the number of lines are leaving. Therefore, while calculating the flux, we do not take the charges which are outside the Gaussian surface. If the charged particle is outside the Gaussian surface, the number of lines enter from here, number of lines leaving from that is the same here. Therefore, the net flux through a given surface is equal to 0, right. So, therefore, while calculating the flux, we always take the charges inside the Gaussian surface. Now, we have one or two examples you can see. For a closed body, outward flux, you see that here, for a closed body, outward flux to be taken as positive, while inward is to be taken as negative. See here, if at all the charge is here, the lines you can see that here, in this case electric field here, and net flux will be equal to positive. The lines of force are leaving only. In this case, lines of force enter into the Gaussian surface and net flux to be taken as negative, because area vector and E vector will be opposite. You see, intensity will be like this, area will be like this, and in this case intensity and area both will be in the same direction. Therefore, it is a positive and here is a negative. And if at all area vector and E vector are perpendicular, the net flux through this one is equal to 0. Let us assume that here this is a one cylindrical surface, let us assume is a cylindrical given arrangement, and once it is placed in the electric field, and here you see that here lines of force enter, therefore, here the flux is equal to negative, here the leaving, the lines of force are leaving, here you can see lines of force are leaving, which is in the direction of area vector, here the flux is positive, here the flux is negative, and here the flux is equal to 0. Therefore, here the flux is negative is equal to how much? EA, A is equal to pi r square E and but negative, minus EA cos theta, theta is 180 minus 1, and here is the flux pi r square into E, positive, and therefore, the net flux is equal to 0, because why the net flux is equal to 0? No charge is inside. The complete cylinder is placed in the external electric field only. Complete cylinder is placed in the external electric field itself. The lines are entering, lines are leaving, 2 lines enter, 2 lines leaving. Therefore, the net flux is equal to 0. In other way, the Gaussian surface also we can say that no charge particle is inside. Therefore, the net flux is equal to 0. Next, you see that here, and this particular case you see that like charge particles are there here. This is a dipole, let us take that here in this case, and the flux from the given surface S1, let us take that here. So, you take that one particular surface here, we have a different surfaces I am taking here, and if you take that first surface is equal to how much? Only this surface I am taking here, only this particular surface. If you take that first surface here, if you take that this particular surface is S1 I call, which is equal to positive, and here is the next second surface is here S2 negative, and what is the flux through S3? This is the one surface I am taking, that another surface I am taking. You see, this is the one surface, third surface is here, no charge particle is inside, the number of lines entering, number of lines leaving are same. Therefore, the net flux is equal to 0, and here flux through S3 as well as the flux through S4 is also equal to 0. S4 is the total this particular surface, right. So, this is the one, here is the one charge particle, children, this is a positive charge particle and here is a negative charge particle. These two are the two charge particles we have. Flux through the first surface is equal to how much? It is q by epsilon naught. Second surface is equal to minus q by epsilon naught. If you take a third surface here, this is a third surface which is outside the charges, flux is equal to 0, and this is a fourth one, the flux is also equal to 0, because two charges are inside, but the net charge is equal to 0. One is a plus q and one is minus q, and the net charge is equal to 0. Next, this is a dipole, children. If at all you take the dipole here, and if you assume that Gaussian surface here and the charge enclosed is equal to 0, therefore net flux is equal to 0. This is one example. Now let us take that one more example. You can see here q1, q2 and minus q3 are inside, and what is the flux through this particular Gaussian surface, which is equal to 1 by epsilon 0 times to q1 plus q2 minus q3. Okay. So, this is about like 2-3 examples related with the flux, and some more applications we have here, we will see. Now, you look at carefully, this is one closed body, it is kept in the electrical field, non-uniform electric field, and the number of lines entering, number of lines leaving are same, therefore, the net flux is always equal to 0. And let us take that here, this particular cube here, this particular cube, and here is also you can see that here the electric field is like this, the cube is here, the number of lines enter from here, number of lines leaving here is same. If the field is uniform, the cube is placed, and here the flux is negative, here the flux is positive, the net flux is equal to how much it is? 0. Next, if at all the charge particle is kept inside the cube here, and the net flux is equal to q by epsilon naught, and as it is a symmetrically placed at the midpoint of this, and that flux will be almost equally distributed through each face, because for a cube there are 6 planes, we can assume that here through each plane almost equal to 1/6 of the total flux given by that, which is equal to 1/6 epsilon naught into q. So, simple way we can write it, through the entire cube is equal to 1 by q by epsilon naught, through one particular plane is equal to that. This is only one phase here. Next, we have other cases like let us assume that here, if at all there is a cube like this, let us take that here, a cuboid, you take a charge here, the total flux given by what is equal to q by epsilon naught. Only through this, how much in the sense, exactly half of that, q by 2 epsilon naught. The total flux emerges from the system of the 2 cubes is equal to, 2 cubes is equal to here q by epsilon naught, and flux through one particular cube is equal to how much it is, and q by 2 epsilon naught, because if at all the charge is kept here, which is q by 2 epsilon naught. Next, we have other applications, children. What are the applications in the sense, earlier we discussed till now 2 electric field intensities. Electric field intensity given by the point charge we did, electric field intensity given by the dipole also we discussed. Now the next one is a electric field given by the long linear conductor. A long linear conductor, let us take that here, whose charge density is equal to lambda. What is the electric field intensity at a point here, at a distance? This is a long linear conductor, charge conductor like this. What is the electric field intensity at this place? E is equal to lambda by 2 pi epsilon naught into r, where E is equal to, E is directly from lambda, inversely from r. If you take a graph here, E and r graph, it is inverse. These are just formula based, you must remember the formula here. Next, electric field, only electric field here, due to infinite a plane sheet of charge, just a plane sheet of the charge is given as non-conducting sheet, uniformly charged. And in this case, and if you take that here uniformly charged, a charge plate if it is given, and electric flux is equal to how much it is, accordingly we can calculate, but electric field formula only you can see that, children. And this is a one charged body, charge sheet, and electric field intensity at this place is equal to, E is equal to just a sigma by 2 epsilon naught, sigma by 2 epsilon, which is a non-conducting sheet. If it is a conducting sheet, what happens, we will see that here. And electric field due to the 2 infinite plane parallel sheets of the charge. This is a 2 plates are taken here, this is a positive charge, this is also positive charge, sigma and sigma are taken here. Due to them, electric field intensity is equal to 0 here, and outside is equal to how much, and this side is also how much. Here intensity given by this, intensity given by this, equal and opposite, they get cancel each other if at all they are equal charge densities. But here the charge density of this one is sigma A, and the charge density of this one is sigma B, which is given here. Therefore, the electric field intensity at point P is equal to, due to this, it is away, because positive charge away, due to this also away. And at the same time here is also due to the negative, this is a positive charge away, due to this positive charge away, the net electric field here and here magnitudes are equal, opposite you can write as 1 by 2 epsilon naught this. This is also same thing, this one and this one are same, but only thing is this one here at this place, due to this to the right, due to this to the left, they are opposite to each other. If they are equal in sigma, then it will be 0, it is a null point will be created. Next, other one, if at all electric field, we are discussing about the only electric field, due to the conducting sheet, point to be noted, conducting sheet, earlier is a non-conducting sheet, just a plain sheet of charge, this is a conducting sheet. Conducting sheet in the sense, whenever the charge is given to this, charge will be residing both the sides, therefore it acts as a 2 non-conducting sheets. Therefore, electric field intensity at point P2, electric field intensity at point P1, both are equal in magnitude, opposite in direction, this is away and this is away. Therefore, the net electric field intensity at this place is equal to, due to this set of charges is this, due to this set of this charges is equal to this, both are equal and up in the same direction, you see that here. Therefore, the net intensity is equal to sigma by epsilon naught. In case of conducting sheet, non-conducting is sigma by 2 epsilon naught, and net resultant field is equal to what here, 0 inside the material, inside the material always electric field intensity is equal to 0, net flux is equal to 0. This is outside. Now you see that electric field due to the charged hollow sphere we are taking, Let us take that this is a one hollow sphere or conducting sphere. In case of conducting sphere or hollow sphere, whenever the charge is given, charge will reside only on the upper surface, charge reside, and here like this, and therefore what is the flux due to this, what is the electric field intensity outside? Formulae, you can take that intensity at outside and intensity on the surface, which is a maximum, and inside is always equal to 0, children. Inside is always equal to 0. Electric field intensity inside is equal to 0 here. Inside is equal to 0. Therefore, the graph will be like this, children. Now, electric field up to the small r, and where E is equal to this and small r, and intensity go on increases suddenly and gradually decreases. Okay. So, this is what actually intensity due to the conducting sphere or and hollow non-conducting conducting sphere uniformly charged. In that case, and electric field intensity is equal to 0 inside, only outside will be there, and outside how it is inversely proportional to r square. Same thing here, and this is a uniformly charged non-conducting sphere. Non-conducting sphere in sense inside the field also will be there here, only at the center the intensity will be equal to 0, and the intensity at everything outside is the same, children. Outside is the same, on the surface also the same thing, on the surface also the same thing, but only inside is equal to what actually 1 by 4 pi epsilon q r by r cube, where intensity is proportional to small r, and outside is equal to inversely proportional to the r square. It is directly proportional, inside directly proportional to r, outside is inversely proportional to r square, the intensity. These are the applications of Gauss law here. Okay. So, that is all, almost the end of the topic. One small point here you can see, and mechanical force and a dielectrical pressure on the charged conductor here. Whenever, let us take that here any particular one you can see, and simply you can say that here when a conductor is charged with a charge q, and on the surface how much the force will be experiencing, what is the pressure on that, we can say that here this pressure is equal to this 1 by 2 epsilon naught into E square. So, this is about electrostatics, children, electric charges and fields, and let us see that now the gravitation, right. Next to the Babu. Yeah, children, till now we did about electric charges and fields. Now continuation with the gravitation, and gravitation is also direct formula based topic, and mostly focus on the concepts and related important models, you can see that. Okay. So, mainly I am stressing on the concepts only in this chapter. If you really remember the concept, you can do the problems. Okay. Right. And at one stretch we will see that even gravitation. Now, in the gravitation different segments here, the first one is the Kepler laws of planetary motion, where there are 3 laws of planetary motion here, and according to the first law, all the planets are revolving around the sun in an elliptical orbit. The angular momentum of that particular planet remains constant here, and and sometimes the planet is closer to the sun, sometimes far from the sun, and as distance changes, speed also changes. How the distance and speed changes here, v is inversely of r, and angular momentum remains constant here, and where this is called what actually perihelion, this is called the aphelion, we can say that the closest point is said to be the what actually you see, and perihelion, and the farthest point is said to be the aphelion. This is the first law. Now, the second law says that here, and aerial velocity remains constant when the planet revolving around the sun, area covered per unit time is always same. Delta A by delta T remains constant. Delta A by delta T is equal to L by 2m is always constant, right. So, that is all about the amount of area covered per unit time is always constant. Area swept by the line joining the sun and the planet, it cover equal areas in equal intervals of time over. And third law here, when the planets are revolving around the sun, the time taken by the planet to complete one revolution is said to be the time period of revolution, and the time period, the square of the time period is directly proportional to cube of the main radius, and many applications are there based on this. T square is proportional to r cube. As r changes, accordingly the time period also changes, and here we say that T square is proportional to r cube, and T1 by T2 square is equal to R1 by R2 whole cube, we can say. And if at all, and the change is very small, if the radius of the orbit slightly changes, just 2%, 3% only changes, in that case we go for the binomial expansion. From that you are going to get delta T by T, the percentage of change in the time period due to change in a radial distance, and which is equal to 3 by 2 times to delta r by r, we can write it, because t is proportional to r power 3 by 2, and we have a relation here, y is proportional to x to the power of n. Whenever percentages are less than 5%, approximately delta y by y is equal to n into delta x by x, we can write it. That is all about the Kepler laws, and we have two simple problems are there. You can check that here, very simple one. If the radius increased by 20%, what is the percentage of change in the time period? Radius increased by 20%, you can take that here. If r1 is equal to 100, r2 is equal to 120. And percentage of change in the time period I want to calculate here, which is equal to T2 by T1 is equal to 1.331. Percentage of change formula, you know children, in any part of the science, percentage of change is change by original into 100. We can write it, which is equal to approximately 33%. If the radius increased by 20%, the time period increased by approximately 33%. Next, the same question, similar way, in the other one you see, if the radius of the orbit increased by only 2%, earlier I gave you 20%, here the 2%, which is less than that of 5%, then we go for this particular concept here, 3 by 2 into delta r by r, which is 3 by 2 into 2%, approximately 3%. Okay. Now, that is all about Kepler law. Next, this is also similar kind of the question, you can try it. Now, the same, universal law of gravitation. Universal law of gravitation, like electrostatics only, that is a Coulomb's law, and here the gravitation law. And what is the difference between them? There, Coulomb's law of electrostatics depends upon the medium between the two charges. Gravitation, universal law of gravitation here, and a gravitational force between the two masses independent of the medium between them is always universally constant, which is equal to F is equal to magnitude of the force is equal to G m1 m2 by r square. What is the G value is given, and a simple problem that we have here, and the three masses which are kept, again force is a vector. This particular one I asked that here, gravitational force on C I am asking, gravitational force on C, because of this is attraction, and because of this there is attraction here, and the net force will be like this, net force will be, and what is the net force is equal to R is equal to 2f cos 60 by 2, the same root 3 times 2 g. This is one of the simple problem based on the gravitation, universal law of gravitation. Now, this is also another kind of the question here. In this case, find the distance from a 2 kg at which gravitational force on 1 kg is equal to 0. See, here the two masses are kept, 2 kg and 8 kg are kept here. He is asking at what distance a 1 kg mass is placed, this is a 1 kg mass is kept, so that it does not experience any force, indirectly that null point. Null point concept only we can apply here. In the electrostatic, just now we discussed, in the last slides we discussed about the electric field, where electric field intensity is equal to 0, null point. The same thing here, x is equal to r by under root of m2 by m1 plus 1 with respect to m1 children. Directly you can use this formula, otherwise this force and this force are equal, get cancelled, and x is equal to 4 meter. Okay. Now, the next one, relation between the small g and capital G. So, small g, in case of planets we say that here acceleration due to gravity, that is gravitational field intensity only, indirectly gravitational field intensity given by the planets. And our planet, the acceleration due to gravity changes from place to place. Similarly, every planet has got its own g value. Capital G is universal constant, small g varies with the different parameters. And let us take that our planet here. It is almost like a solid sphere, and since it is a solid sphere here, mass is uniformly distributed inside, and where the acceleration due to gravity on the surface is highest, as we go up decreases, as you go down also decreases. I simply, we know that very well known formula, you just refer that. G at a height h, g at a depth also I gave you, g at a depth is equal to this. And how the g value varies inside, directly proportional r, at the center is 0, on the surface it goes to maximum, and outside the gravity slowly decreases, right. It is similar to that of electric field intensity in case of non-uniformly conducting sphere. Non-uniformly, like whatever that non-conducting sphere. In case of non-conducting sphere, also the same thing here. Electric field inside is not equal to 0 all the ways. Only at the center it is 0. As you go to the surface, intensity slowly increases and outside decreases. Similar way here is also, we have a simple graph, and this is a previous NEET question only, you know that this graph. Next, coming to the point here, And electric field intensity, we did not use any kind of the concept about the latitude, but in the gravitation we have about the latitude. And because our planets are revolving here, because of the rotation, let us take that here, and angular velocity is equal to omega. At a given latitude, due to the angular velocity, there will be a variation of g. And what is the g at a given latitude is equal to, at this latitude is equal to, what is the g here? This is called the latitude, this is called the latitude here. And at a given latitude here, which is equal to g minus r omega square cos square phi. What is g? G is the acceleration due to gravity at the poles, r is the radius, omega is the angular speed, and phi is the latitude. Is the latitude is same at all the places? No. At equator it is almost 0. At the poles it is 90 degrees. Therefore, at the poles is equal to how much it is? G value is equal to how much? Just g only. And at the equator is equal to g minus r omega square, because cos square phi is equal to 1, phi is equal to 0. So, therefore, here g at equator, g at the poles, g at a given latitude. Now, I gave you one question, you can see, find the angular velocity omega I calculated, and for which the angular velocity at the equator is equal to 0. We are going to get that here if you substitute here. You substitute, all values are substituted. Radius of the planet, radius of earth, you know, radius of the earth is equal to 6,400 kilometers approximately, 6,400 kilometers. And when you substitute all these things, you are going to get that angular velocity must be equal to, that means our planet should rotate with an angular velocity omega, which is equal to 2.5 into 10 power minus 3 radian per second, for which the acceleration due to gravity at the equator becomes 0. Now, coming to the next. Here, find the height at which g is 36% less than that of the surface. As we go up, g value go on decreases. We need to find out what is the height at which g value is 36% less than, 64% only it should be, because 36% less in the sense left over is 64%. You can see g at that place is equal to only 64, 36% gone, and substituted here in place of that, this is a g value at a given height is a very well known formula, and from that we can find out here h is equal to r by 4. And the next one, similar way, find the ratio of g at a, you see that here on the two different planets of masses are in the ratio 1:2, densities are in the ratio 8:1. And in this case, you please look at the formula here, small g is equal to, on the surface children, one of the formula which is equal to gm by r square. This is in terms of mass and the radius. The same formula can also be written as in terms of 4 by 3 pi g r rho also can be written. This is in terms of what actually here, r and rho. G value on the surface is inversely proportional to the r square provided m is constant. G is directly proportional to r provided the density is constant. Based on this concept, here mass is also involved here, and how the g value changes on the two different planets, and a comparison of g values on the different planets, you can substitute and you are going to get it. Next, gravitational potential energy. Gravitational potential energy in the sense, because you know, and the gravitational field is a conservative field. Whenever the two masses are kept at a certain distance, and some field energy gets stored here, because whenever the two masses are at a far distance, no influence of each other, whenever they are bringing close to this, what actually we are doing the work against the gravitational force. Whenever we are doing the work against the gravitational force, some energy gets stored here. That energy is equal to potential energy, which is equal to minus g m1 m2 by r square, because we are doing the work in the direction of attraction force only. That is the reason minus. Okay, minus g m1 m2 by r square. This is a potential energy between the system of two masses. Any number of pairs are given, the same amount of force will be there accordingly, and potential energy also will be there here. Now, in case of planets children, in case of planet, let us take that here. This is a planet. Let us assume that there is one particle of mass m. What is the potential energy of that particle of mass m on the surface of the planet, which is equal to potential energy of object at a point A is equal to this on the surface. What is the potential energy of the same object which is at a distance smaller from the center, which is equal to this, which is smaller is equal to Kepler plus h. And what is the potential energy of the same mass at infinity is equal to 0 as the distance increases to infinity. And inside here, inside if we take that here, which is equal to minus gm by 2 r cube, 3 r square minus 2 small r square, you please remember this formula inside. Potential energy of a body of mass m which is kept at a distance small r inside here. At the center, potential energy is equal to here, small r is equal to 0. In this formula, small r is equal to 0, which is equal to 3 by 2 times to the potential of the body on the surface, potential energy of the body on the surface here. Okay. Now, based on this, some questions are there, and let us take that here. Whenever the object is moving, this is one concept, whenever the object is moving under the influence of gravitational force only. For example, if this object is dropped, it is moving under the influence of only gravity, assuming that buoyant force is ignored, viscous force is ignored. Whenever the body is falling under the influence of gravity, or if a body projects vertically up, in both the cases body is moving under the influence of only gravity. In that case, the total energy remains constant, mechanical energy is constant, potential energy plus kinetic energy is constant. And based on that, we have a certain question here. A mass m is dropped from a height h. Here see that h is equal to r only. Radius of the planet is also I am taking as r, and therefore from here to here is equal to how much is small r is equal to capital R plus capital R, which is equal, because from here to here is equal to r plus r, which is equal to r here. We need to find out here what is that the speed with which this object which is dropped here, when it reaches to this place, what will be the speed. Simple law of conservation of energy. Here potential plus kinetic, here the potential kinetic, and I substituted same thing. You can see that here, and V is equal to capital Gm by r, or else if at all in most of our gravitation question, children, sometimes options will be given in terms of capital G or in terms of small g. Wherever capital Gm is given, we can write as small g r square. Next. And this is the potential in the system of these two masses here. Find the potential system of masses. How many pairs are there? At every pair potential energy gets stored. Here the 3 pairs, we have 3 masses. Here is a 1 pair, this is a second pair, and this is the third pair. And we got that same thing. This pair, if you take that here, simple I wrote that here, minus g m1 m2, 1 into 2 by the distance is 1 meter. If you take that this one, 2 into 3 by 2, and third one is equal to 1 into 3 by 3, we get that minus 6g. And the next second question we have, what is the work done to shift 3 kg mass to infinity? Here the 3 masses are there. What is the total work done to shift this one here, to shift to the infinity? Change in potential energy. Whenever this mass is taken to the infinity, and what is the final energy you can calculate, what is the initial energy, and work done to shift one object from one place to another place under the influence of conservative fields and change in potential energy. Directly we can write it as 4g. Now, and similar concept here is also, this is an important concept here. 3 particles are at 3 corners of equilateral triangle of side L. What is the work done to increase the size of the triangle? To increase the side of the triangle to 2L. Earlier the side is equal to L. Now the side is equal to how much? It is 2L. Side is equal to 2L. And for this, what is the amount of work done is equal to change in potential energy. Earlier what was the, see the formula. Earlier what was the potential energy? Minus GMM by L. 3 parts are there, 3 pairs are there here. This is the original potential energy before they shift. After shifting here, the new potential energy is equal to this, because the side is equal to L. Earlier the side is L. So this is a new potential energy of the system. This is the original potential energy of the system. The difference is equal to amount of work done. Even if you decrease the distance, also same concept. Final energy of the system minus initial energy of the system. Next. Here, that's all about the potential energy, children. Now let us take that here the 2 important velocities we have. One is orbital velocity, other one is escape velocity. What is orbital velocity? Let us take that here. You have one object, you are on the surface of the planet, you are at the top of the building, and you throw a body with a certain velocity. The body reaches to the ground. If you go on increase the speed horizontally, at one particular minimum velocity, body revolve around the planet, where centripetal force balance with the centrifugal force. Therefore, that particular velocity is called orbital velocity. And in case of orbital velocity, what actually here, and the centripetal force, centrifugal force are balanced, and orbital velocity is equal to, at a distance r, orbital velocity distance small r is equal to under root of gm by small r. Or else, no sir, you want the object to revolve very close to the surface of planet. In that case, small r is almost equal to capital R, where gm by capital R, or else we can also write, just now I told you, in terms small g also we can write it. and orbital velocity depends upon the mass as well as the distance. And in case of Earth, on the surface of the Earth, orbital velocity approximately 7.92 kilometer per second by substituting mass of our planet, radius of the planet. Okay? That is orbit. If at all the velocity more than that, what happens? And different cases we have. If at all the velocity less than that of this, it definitely reaches to the ground. Okay? And one more velocity which is called the escape velocity. And orbital velocity must be projected horizontally, no doubt. And escape velocity, children, you can see whenever you have an object on the surface of the planet, you project the body with a certain velocity, the body never come back to the ground, it escapes from the gravitational field, which is called escape velocity. And that escape velocity never depend upon the angle of projection, whether it is projected horizontally and vertically upwards at a certain angle, no matter, and escape velocity depends upon only, and you can see that what are the concepts here, depends upon what actually, is it depends upon the mass of object? No. Is independent of mass of object, depends upon the mass of the planet and also the radius of the planet. You can see escape velocity is equal to under root of 2 gm by r. For Earth, in case of Earth, what is the escape velocity is equal to 11.2 kilometer per second, which is almost root 2 times to the orbital velocity. Root 2 times in sense approximately 1.414 times to orbital velocity, 41.4% more than orbital velocity is the escape velocity. Coming to point, there are two important formulae here. If at all the body projected vertically upwards less than escape velocity, can it escape? No. It go to some maximum height and again come back. What is the maximum height it will go and come back to the ground in the sense? This is the formula here, children. You can see what is the maximum height it will go. If at all the body projected with a velocity less than that of escape velocity is this, and r into k square by 1 minus k square. For example, v is equal to 1 by 2 into ve. That means k is equal to how much it is? 1 by 2. Example here. If at all you project the body less than that of escape velocity, it goes to some maximum height and it come back, and one simple question is there, you can see the same question is given, it go to the r by 3 and come back. Or else, if at all the body projected with a velocity more than escape velocity, what happens? Then you please look at carefully, and it leaves that zero gravity, here zero gravity with a certain velocity, velocity at a infinite point is equal to escape velocity into under root k square minus 1, ve under root k square minus 1. This one is equal to r into k square by 1 minus k square. This is the velocity. I will repeat once again, if at all you project the velocity, I give you concept here also, you see, if at all the velocity v is k times to escape velocity, which is k is greater than 1, in that case v at infinity is equal to v under root k square minus 1. Now based on that only this problem is constructed, where k is equal to 2 times root 2 times, therefore the body leaves zero gravity with the same equal to escape velocity. Next, see children, the satellites. In case of the satellites, you see here they have a orbital velocity because the rocket is used to launch the satellite, and the satellite in a particular orbit will have some orbital velocity. Respect to orbital velocity, it has a kinetic energy, it has a potential energy, it has a total energy. As the object go away from the planet here and the total energy go on increases, kinetic energy decreases, potential energy also increases. Now let us take that here. And what is the potential energy of the satellite at a certain distance? Is orbiting. Satellite is not at rest. It has a kinetic energy, potential energy and total energy. Potential energy of the satellite minus gmm by r. Kinetic energy of the satellite is equal to half of the potential energy but minus, and which is equal to gmm by 2r. And the total energy is equal to this minus gmm, sum of potential and kinetic. And the graphs here we can see this is equal to kinetic energy graph, which is always positive side. And this is a total energy, this one and this one are mirror image because they are equal in magnitude. You see minus gmm by 2r is E, k is plus gmm by r. But here you can see that here this will be equal to far away from this, where potential energy is equal to minus gmm by r. The graph between E and r, potential, kinetic and total energy. And this is one of the important concepts. You can see we have a problems, work done to shift the satellite, because you see children, work done to shift an object. Here I want to find give a small information about this. The work done to shift this object from here to here is equal to what? here no change in kinetic energy, only change in potential energy we take it. But satellite already in the orbit, if that satellite to be shifted to another orbit of another radius, so naturally what actually here it has since we are mentioning that is a satellite, it has both potential energy, kinetic energy, therefore we need to take the total energy into the consideration. The amount of work done to shift the satellite from one orbit to another, which is equal to change in total energy. Okay. Now coming to the point, based on that only one simple question is given. You see here, a satellite of mass m is in the orbit of radius 2r, and what is the work done to shift this satellite to the orbit of radius 3r? Earlier it was in the radius 2r, now wanted to shift to that of radius 3r, and while studying about this particular point here, whether height is given and radius is given, you must see that I clearly gave that radius only, and earlier it was in the radius of orbit 2r, now the 3r, and by taking that E2 minus E1 you are going to get that work done to shift the satellite is equal to, we can write as mgr by 12, because I eliminated capital Gm, it taking the capital Gm is equal to small gr square, we are going to get this. Okay. So these are the important concepts about gravitation, children, and almost these are the concepts are very much sufficient for doing NEET effectively, and electrostatics and electric charges and fields and gravitation, most of the things are almost same, and please relate yourself, and what are the models that are given, you please focus on that. Is it clear? And definitely this topic will be much helpful and you can expect the good marks. All the best.